Hello, it's Keith here, and this is the second episode of the Grime 68000 project, in which I try to convert Grime Z80 to the 68000 programming language. Of course, I've just recently converted it to the 6502, but I am going back to the original Z80 code when I'm converting the 68000 version, so let's see how we're doing today. Well, this is of course the second day, and you can see how the code is looking today, and basically I've got the title screen working with the scrolling message working. Now of course it won't be clear from this, but I have actually got the double buffering, which is the two copies of the Tilemap, and only the differences are being drawn to the screen, but you can't really see that from what we're looking at today. Now you can tell from the top and the bottom version that I've got some pretty major speed issues here. The top one is running far too fast, and the bottom one is running pretty much the right speed. I can also see there's some occasional glitches on the top one. I don't know if this is something to do with interrupts, but obviously that might be something I need to look at later, because I don't quite know why the text is kind of juddering occasionally. But anyway, things are working pretty well, and hopefully they're working on all of the systems. You'll also notice I've now centralized the screen on all the systems, because some of these screens are more than 256 pixels wide, but the game is designed for a 256 by 192 game area. Now, the X68000 version was working at 512 by 256 yesterday, which was completely inappropriate. It's now working at 256 by 256, which is the closest as I can get to the 256 by 192 that this game wants to work at. But you can see it still looks a bit squashed, unfortunately. But I don't think there's very much I can do about that at this stage, unless I actually change the size of the tiles, which I don't really want to do at this stage. So anyway, you can see the game running on the X68000 here and the Neo Geo. Let's see if it's working on the other machines. So here you can see the Genesis version, and it's of course working the same. Very good. And here's the Atari ST. No problems it looks like here. And the Amiga version also appears to be working okay. So we've got the game working on all the systems. The font is the same colour on all of them, which means it's using colour 15, which is how I want it to be working. And the image is centralised, irrespective of the actual physical screen size on all the machines. And hopefully everything's generally working okay. As I say, there does seem to be some kind of glitching with the Neo Geo version, and I suspect that's interrupts or something like that. There is one interesting thing about the Neo Geo, and I'm not aware it's affecting it, but in order for the Neo Geo to work correctly, you have to intermittently do something called kick the watchdog. Now what this means is there's a watching process on the Neo Geo that checks if the machine has crashed, and if it has, then it forces the machine to reset. And the way you avoid this is you kick the watchdog intermittently. So we do have to do that, and I'm doing that in this pause loop here. I'm not aware that would be causing any kind of problems, but I can't rule out that maybe there's some kind of bug in my code, because I would have thought that the registers were being protected sufficiently that wouldn't cause a problem. But, you know, maybe it's something to do with that. I'll just have to keep looking at it and see if it causes any of the problems until I figure it out. Anyway, so you can see that all we've got so far is the title screen working, the scrolling message working, and basically the two tile maps working, and of course the tile graphics. So we've not really achieved any kind of game yet, but we have at least made some progress with regards to, you know, the title screen and the graphics are working. So we're on to a good start anyway. So what I thought we might like to do today is we're going to compare the title screen code on the Z80 and the 68000, so we can see how I've converted it. Because in the same way as with the 6502, I have directly copied pasted the Z80 code in and then converted it to the 68000 equivalent. So let's have a look. Okay, so on the left hand side here we have the 68000 code, of course, and on the right hand side we have the Z80 code, and we're going to start looking from the title text reset command here, and we're going to look down and we're going to see what we're doing. Now, if you missed yesterday's episode, the way I'm doing things is I'm converting the Z80 registers to a 68000 register. So I've got my kind of lookup table here, and so whenever I'm using the accumulator, I'm using register D0. Whenever I'm using BC as a pair, or B on its own, I'm using D1. Or if I'm using BC as a address, I'm using A1, because only the address registers here can be used for address lookups and writing. If I'm using DE as a pair, or D, I'm using D2, or A2 if I'm using it as an address. HL or H, I'm using D3 or A3. C, I'm using D4, E, I'm using D5, and L, I'm using D6. And of course, I'm going to be using these if it's 8-bit, or these if it's 16 or 32-bit. So let's have a look at the code. So you can see the labels are the same, but after that everything gets a bit weird. So when I set C to 0 here, we're using the clear command here, and even though in most of these cases I only need to clear bytes, I am actually at this stage clearing the entire 32-bit register just for safety, because the registers having remaining data in them can cause unpredictable problems, but also because later I'm going to add D5 to a address register, so I do need to make sure all 32 bits are cleared here. L stands for long. You can have a B, which means byte, W, which means word or 2 bytes, and L, which means long, which means all 4 bytes, 32 bits of the register will be cleared. The important thing, if you don't know about 68,000, is you can work at each stage in a different length, so you can do comparisons at the byte level, additions at the byte level, additions at the word level. But the problem is when you do that, you may have junk in the higher bits that you've not cleared, that you've forgotten are there, and then if you do a long comparison when you've only ever cleared it at the byte level, you will start getting errors because the entire word is not clear or the entire long isn't clear. So that's something very important to understand, and it will cause you problems. So then I'm moving the byte from D4 in here to D1, and this is because we're copying C to B here, and if you look at my lookup here, C is D4 and B is D1. So we're doing a lookup here, but the important thing to notice is whereas in Z80 it's the register on the right goes into the register on the left, on 68,000 the register on the left goes into the register on the right, so it's backwards, which is quite a pain, but hopefully we'll not make too many mistakes. Now, there is no inc command, rather strangely, on the 68,000, but there is a command that is as good. It's called add quick, and it can take a value from -8 to +7 or something, I think it is. I can't quite remember. Anyway, it's a single byte command, so even though it looks quite long and it doesn't look as efficient as inc-b, it is the most efficient command you can get for increasing by 1, but it can also inc by 2 just as fast. So it's a very good command. So this is effectively our inc command, and we're only working at the byte level. Now you can omit these .b's, and I think it tends to work in long words. I'm not quite sure, but for safety I'm always specifying whether I'm working in B, W or L, because I've made that mistake before, let's be honest. So I'm going to be as thorough as I can and always try and specify byte, word or long where there is an option. In some cases, like load effective address, you can't load the effective address, LEA that is, sorry, that you can't load the byte effective address because the addresses are always 24-bit, so that's not going to make any sense. So in all other cases where there is any doubt over what it should be using, I'm specifying what to use just so I know what it's using and no mistakes happen, hopefully. So we're incrementing our D1 register here, then we are loading the screen width into D0, and you can see that we are doing the same here because D0 is my simulated A. Then we're subtracting the byte here, D4, which is our C, from D0, which is our accumulator. And then we're doing a branch if carry clear here to text not too long, which is the equivalent of this NC here. Now, unfortunately, I have to be honest and say I made a mistake earlier today, and it cost me about an hour or two of debugging. There is a lot of extra branch commands within 68,000, and one of those is branch if positive. And I thought, getting clever, oh well, if it goes above 0 then it's positive, so I can use that instead of branch carry clear. It's a bit more clear that is it positive, has it gone below 0? But I wasn't thinking. I was thinking in 32 bits, but my subtraction was in 8 bits. So the branch if positive was only considering if the byte was from 0 to 128, whereas if the byte went over 128, or including 128, sorry, it would be considered negative. And this is part of the code that cycles the text around. So the text repeating was only working if the string was under 128 bytes. And it took me forever to figure out. I was convinced the problem was with this part, which is where it sees if the text needs to be reset, because it wasn't working. But it was actually all the way up here with this comparison. So, lesson learned. You've always got to think, are you working in bytes, words or longs? And obviously, and 129 as a byte is actually technically negative. If you don't understand that, I've got another tutorial about hexadecimal that tries to go into that. But it was something that caught me out because I've never seen this branch positive command before because Z80 doesn't have it. But anyway, so we're now using BCC, which is the equivalent of this NC here, but I believe is actually the opposite of 6502. That would be BCS in 6502, so it seems the flags are backwards in 6502, which is something I'd noticed before, but I had assumed that 68,000 would match 6582, being as 68,000 was the successor to 6800, and the 6800 was the basis for the cut down 6502, but apparently not. So yeah, just catching us out there, plenty to learn. So then we're loading in the screen width here, and we're moving that into D1. Then we're moving D4 into the accumulator. Now, of course, there's a lot of redundancy here. Because I'm copying the commands literally at this point, there's a lot of things that the 68,000 could do far better. But at this point, I'm not too worried. I'm not sure the game's going to need speed optimizing at all. It's probably more likely to need slowing down. But, you know, I might decide to get very particular and try and optimize the code to make it more efficient, so if I have time. So as I say, at the moment, don't assume this is the best way to code it. I'm just comparing 68,000 code to Z80 code, and I've copied it as literally as possible just to make it easy on myself. So then we're subtracting the screen width from the accumulator here, and we're moving that into D5 to calculate the amount of characters to skip. Now, of course, you probably could guess that I could put D5 in here and here because the 68,000 can do that, whereas the Z80 cannot. So we don't need to use D0 here at all. Even though I'm using D0 to emulate an accumulator, the D0, D1, D2, all the way up to D7, they're all equals as far as the 68,000 go. None of them have more power than the others. It's not like the accumulator in the Z80 and the 6502. The only important thing is the address registers can do things that the regular registers cannot, and vice versa in some cases. So, as I say, I'm not pretending this is efficient code. I know it categorically isn't. All I can say is it does seem to work, which, being as the speed that I've written it with and my inexperience with 68,000, I think is good enough at this stage. So here we're just loading in the accumulator into our fake H register, which is D3. Then we're loading in the screen height. The locate command is, of course, using D3 and D6 as emulations of H and L, because I'm, again, mimicking these commands as close as I can. Then we're loading in the address of the scrolling message. Now you'll see here we're using a LEA command, load effective address. This is something very, very important about 68,000. Unfortunately, we're not in Kansas anymore when it comes to the addressing modes on our system. When we work in Z80, we tell the system this is going to load into the memory address 1000, and we are kind of in control very much about what really happens when the program starts, and we can really take over the entire operating system, flush out the firmware, and just really run riot. We can't do that with 68,000. 68,000 always has an operating system. It has processor modes that are above us that we can't access in most cases. It has debugging tools where the processor will hard run to traces automatically, which is great, but it means we don't have the same power as the programmer. We can't really just flush out the operating system, do everything ourselves, take the memory however we want it. We can't really do that. There's protected memory areas and all kinds of things. The later ones could do, I think some of the later ones could do multi-threading, and they would have virtual work memory areas and predictive execution, which is all of the stuff from the modern processors, of course. So we are into a very different world now with 68,000, and the point I'm getting to is we don't even know where our program's going to load into memory. We can't decide. According to the compiled code, I think this all loads into 0, but it doesn't load into 0. The operating system will decide where it's going to put our program, and then it will give us the program some memory. In some cases, if we use labels and jumps, most of these jumps are actually relative, but in some cases where we do a literal jump, the operating system will alter the code within our assembly language, within our compiled assembly language, and it will alter the addresses to the real addresses in memory, but in some cases it won't, and so that's something we have to be very careful of. If I had done a move and moved the address into the address register here, that would work on some operating systems where the addresses are altered dynamically, and on some it won't. I've come across that before. I think maybe the Neo Geo doesn't do it, but the X68000 does, or something like that. Moral of the story is, if you want to access data within your program's code, always use LEA for load effective address or PEA for push effective address, which will put the address onto the stack. So that's something very important. Okay. We're going to come back to that in my tutorials when I actually get around to that. But anyway, so, and then we're adding D5, which is the offset within the message to the message address. We're clearing D0. I'm clearing all the bits again as safety because I was having trouble. Then we're moving a byte from A3. Now you'll notice here we are doing a dec HL and then loading A from HL. And these two commands here are the same as this one command here. The negative here before the address in brackets means decrease the address before we read from it. And this is the power of 68,000. We can increase addresses after reading from them and decrease addresses before reading from them just by putting a minus before or after the brackets. And this is really something quite impressive about 68,000, and it means that we can save a lot of speed. And this is the irony, of course. 68,000 is not just a faster processor, it's a better language as well. So you win on both strikes, you know. And then we're doing comparison. Of course, again, we don't just have to be able, we can't just compare to the accumulator. We can compare to any of our registers now, but we do need to specify we're comparing at the byte level. And you'll notice we need a hash whenever we use a literal value, just like 6502. It's the same with the hash defines a fixed number and the dollar defines hexadecimal. And if we don't use the hash, we would use an address. And as I've already said, that's very risky with regards to this relocatable code. So we're jumping to a service routine here for print chow, and then we are decreasing D1 here, which is our B value, I believe. I'll double check that. That's our B value, yep. And then we are branching out to the next one if we've not reached 0 yet. So just printing all the characters. Here's our delay. We're loading 40,000 into D1. We need a lot of delay, and we're jumping to the pause command, and then we're repainting the screen, and then we're looping back up. And that's just an infinite loop. Star means the current line. Jump to the current line means it goes round and round in circles forever. And then our pause command, you'll see I've actually nested another pause command within the pause command because it was so fast I had to work to slow it down enough. So I guess I need to use some kind of interrupt to slow it down because this is going to be very CPU dependent, but for now it'll do. So I'm just branching, I'm using this D branch, which is decrement and branch, which it sounds quite similar to dbnz, but unfortunately it's slightly different. dbnz ends when it reaches 0, dbra ends when it actually goes below 0. dbnz would run one less time than dbra, so you do have to be careful that you understand that dbra doesn't actually work exactly the same as dbnz, even though it's similar. So anyway, and then you can see here's our kick watchdog command, which I'm sure PETA will be very upset about, but never mind, we don't care what they think. And then we're just doing a loop here. So there's two nested loops just to slow things down enough to try and get things functional. And I mean, it's kind of working. Kind of isn't, but it's kind of working. So I still need to slow it down a bit more, but it'll do for now. So there we go. So that's what we've got today. So hopefully we'll be doing some gameplay tomorrow. I maybe will be able to get some joystick controls going in and maybe a moving object or not. We'll have to see. Anyway, I hope you've enjoyed today's episode. Please join me for next time. It'll be on Patreon tomorrow or on YouTube in a week's time. Of course, you can always watch the 6502 or the Z80 series if you are really hankering for some more content. Anyway, thanks for watching today and goodbye.